Perfect. Okay. All right. Hello, everyone, and thank you all for braving the rain to come listen to Niki. So Niki has, did her PhD with Ranjit Jalla at UCSD, and now she's a researcher at IMDEA in Spain. And for about the past decade, she's worked on refinement types, which, sort of on my theorist hat on, they're one of the fundamental concepts in semantics. But like what she's done is bridge this theory and the practice to build the Liquid Haskell tool. And I think she's going to tell us a bit about the work she's done in the past decade. Thank you.
Thank you very much. So thank you for coming. Yes, I will be talking about refinement types and my work. So let's start from the basics. So refinement types refine types of an existing programming language to express concepts that are not expressible in the basic type system of the programming language. And our running example for the refinement types is safe indexing. And I will be using Haskell notation, right? So I have the existing indexing type for Haskell that says, give me as input a list of A's, give me an integer index, and I'm going to give you back the ith element of the list, right? So we can use refinement types to express that safe indexing should be safe. And what we do is we give a name to the input list, we call it x's, and we refine the index to be within the bounds of x's. So we say that it has to be between 0 and the length of the list. So Liquid Haskell is a refinement type checker for Haskell programs. And this safe indexing and other refinement types for basic Haskell operators come built in with Liquid Haskell. So I could have a video, but I think I will persuade you more if I give a demo, a small one. So Liquid Haskell is a GHC plugin. So the only thing you should do if you want to use it is turn on the Liquid Haskell flag, right? And then when you build with GHC your project, you run Liquid Haskell on the back. And as we said, indexing comes with the refinement type precondition. So if I try to index x's with I, I'm getting refinement type error. And we are very lucky because the error up to now, it's very straightforward to understand. It says that you gave me an index I, and I expect an index that is greater than or equal to 0. So we can fix that if we insert a runtime check, right? We can say if the I is indeed greater than 0, then just do the indexing, else return nothing, right? And we turn it to a maybe. And we see that the errors change, which is a good progress, especially if you're verifying programs. And the error now says, you gave me I expect something that is less than the length of x's, so we make the error stricter, and we say that I should be within bounds, and the program type checks, right? And so Liquid Haskell comes with refinement types for many build operators. Indexing is one of them. The other one, of course, is division. So if we try to use what we took from the list to divide, we get, again, a very nice error message that says, you divided with something, this something should be different than 0. So what we can do is we can use refinement type specifications to express that all the elements of the input list are good to divide with. So we use the special comments to give refinement type specifications, and we can say that the input list has elements that are good to divide with. So we can say that all the elements of the list are values v, where v is different than 0. And again, the error got away. And since we used the refinement type specification, we can even express this safe indexing, and we can say, look, the test takes as input a list x's, and then the index is a value I that is like I is between 0 and I is less than the length of x's, okay? So now we can just come and remove this runtime check. I am going to remove this runtime check. And like refinement types are very good at this. Instead of doing runtime checks, you put them in the preconditions, and you can yes, make your programs faster because they have to, at runtime, check less things. OK, so let's see what happens, right? So a refinement type checker is this box that takes as input a program and a property. And it has a set of, RT is a set of inductive typing rules. And these rules generate a logical condition that is valid when the program satisfies this property. And then this logical condition is fed into an SMT solver that decides its validity, right? So in our example, the property was safe indexing. So the inductive set of rules of refinement types are going to generate a logical condition that says from whatever information you have in the context of safe indexing, try to decide that I is like a good index for the list. So what we saw is that at the beginning, that we had 0 information. The context in which I was calling indexing was true. I knew nothing. And the refinement type checker says, like, this indexing is not good enough, right? So then, when I inserted this condition, this runtime check, I had to prove that from within an environment that I know that I is between 0 and the length of x is safe indexing holds. So like the SMT said, OK, this is trivially true. And this example is important because it shows like a very important feature of refinement type checking, that is that they are case sensitive, right? So verification happens exactly within the branch, within the context that it has collected all the information from the environment. And the second very important feature of refinement types is that they are type-based. And we saw this example that, like, if you have a collection of things, for example, if you have a list of integers, you can use refinement types and refine the elements that exist within the collection, right? So you can describe a list whose values are different than 0, whose values are prime, whose values are all like greater than something. And like this type-based verification lets you verify, like lets you describe the properties of the elements of list or every collection without using for all qualification. And this is very important because in Liquid Haskell's refinement types, we have pushed a lot this idea that all these logical constraints that you fed to the SMT solver should only belong to SMT decidable theories. So we don't have for all, we don't have exist, and all these for alls and existential are pushed into the types. They are done externally, and when you reach the point that you are asking SMT questions, you have purely decidable logic. And this is very important because if you give the SMT questions that are not decidable, you can have this, as Rust and Leno call it, you can have the butterfly effect. Because verification becomes very unpredictable, and it can be the case that if you change some part of your program, then verification can like non-terminate or fail in a totally different part of the program. So yes, like in Liquid Haskell's refinement types, we have like this requirement that everything you feed to the SMT solver should belong to decidable theories. So these are some important features of refinement types. They are SMT automated. SMT receives only decidable questions. They are type-based, so you can describe collections, things that belong into collection without the need of for alls or existentials. They are case-sensitive. And the last feature that we saw is that they are language integrated, right? We saw that Liquid Haskell is a GHC plugin now, which means that it is a part of the compiler. It's essentially called by the compiler. And this is important because if a verifier is part of the compiler, it can have all the nice build tools that the compiler has. So you can run them as part of your project build. You can have all this editor, flight check, integration, and all the features that are built for the compiler. You can have cloud testing support, etc. So refinement satisfy by design all these features. And the reason why they satisfy it is because by design, refinement types are practical. So they are designed with practicality in mind. So let's talk a little bit about the design of refinement types. Yes, Liquid Haskell is about 10 years old. We built it at 2014. But the history of refinement types goes back to 1991. And the first paper with refinement types is this refinement types for ML that was done by Freeman and Penning. And so this paper essentially introduces the term refinement types, right? In the introduction, it says they developed a type system, and we call these resulting types refinement types. So it is built for ML, and so if you read a little bit more the introduction, it says we do not extend the language of programs for ML, and it says only programs which are already well typed in ML are passing this stage of refinement type checking. So essentially, these are essential features of refinement types now too, and the idea is that you come with an existing programming language, back then ML, and the idea is to extend the types of this language so that you reject more programs that violate some properties, while you don't touch the existing language. Like all the runtime semantics, you take them you take them from the programming language. So this is exactly the notion of refinement types that we also use. What we don't use is the syntax of refinement types that they used. So I don't know if I can, yeah, it's fine. So here they have an example of the refinement types, and they present a list. So they use data type to refine a list of A's, and they say it's either nil or a cons. And this rec type is their syntax, their way of defining a refinement type. And they are defining the singleton type that refines list. And by construction, this singleton type is a cons with a nil. So it is a list that contains exactly one element, and it does refine the data type of list, right? So back then, 91, the refinement types are essentially data type definitions. So this notion of refinement types did not make it to Liquid Haskell, but there is a lot of work still happening in this notion of refinement types. And if you want to learn about this, like the paper I suggest is 2017, Extensible Data Sort Refinements. And this paper, of course, describes how to extend data sort refinements. But for me, this was a very good paper to understand these different notions of refinement types, right? And Jana here at the very beginning says, yes, this is not the refinement types of Liquid Haskell, for example, but these data sort refinements refer to the classic form of refinement types, that is data sort refinements. Okay, so yes, data sort refinements are refinements because they, again, refine an existing programming language. Okay, so back to 91, the next important paper in the design space of refinement types is this dependent types in programming language. Again, it's by Fleming and he. And so they, again, design a refinement type system for ML, for the ML programming language. And they call it dependent types, but it is a refinement type in the sense, again, they have given the target language, which is ML, and their goal is to enrich the types of the existing programming language of ML, right? And their suggestion in 1999 is essentially described by this word, is like type indexes. So again, they provide an example with lists, again, data type list, nil or cons, and then they say these dependent or refinement types, they are essentially refining the list type by indexing the data type a list with a NOT. And of course, this NOT is describing the length of the list, right? So nil has length 0, and then con says for all natural numbers, give me a tail, a list of size n, and I'm going to give you back a list of size n+1. Good. This became DML, dependent ML. And then 2006, he called it applied type system that has this idea and it has many more ideas. And the idea is like, how do you do practical programming with dependent types and how do you do theorem proving? And this system, again, like is supported by he, you can find it, it's online. It has a lot of work and information, right? So 2006, DML became ATS, but there was something other. There was another thing that was like very cool that happened 2006. We have this hybrid type checking. Like for me, this is like a very, very big paper. By the title, hybrid type checking. It is hybrid because it combines, like it uses essentially refinement types to define contracts. And then the intuition of this paper says, check whatever you can statically, prove or disprove the contract statically, and whatever you can, inject runtime checks, and they are going to be checked at runtime. So it has this hybrid or gradual or dynamic sense of checking contracts. Okay, so what this has to do with refinement types is that if you go to the syntax session, it essentially defines the syntax that currently we are using in the refinement types of Liquid Haskell. And it says, syntax, you have functions, and these functions are dependent function types. You bind your argument with a binder x, and this x can appear in the result t. And like Flanagan says that he got this syntax from Kayan, and this is equivalent to the Pi syntax of the type theory. And then later it says we introduce base refinement types. Of the form subset type, you have x that describes a value of base type b, and then this x is refined by a predicate t, and like in this hybrid type checking, it says that this t is any Boolean term of your language. Okay, so this is exactly the syntax we use up to now, and in the PLDI paper, Flanagan had some meta theory, but I guess he didn't like it enough. So 3 years later, he revises the meta theory, and he's defining like essentially the semantics of refinement types. So he calls he uses his brackets to give meanings to the refinement types. He called them denotations. I still call them denotations. I guess the type theory people told me I should call them logical relations now. But yes, so he says the denotation of a function type, x of type s goes to t, I don't know, anyway, says that it contains all the expressions e, so that if we apply e to an expression s, where x belongs into the denotation of s, of the argument s, then we get something that belongs into the denotation of the result. And this is quite straightforward for the logical relations or denotations of function types. So what I think is very cool is the denotations of the base types, right? They say that it contains all the expressions E that belong, like, if you check them by lambda calculus, they have type B, but then also if E runtime evaluates to a value V, then this value should satisfy the predicate T. And like this satisfy says T, if you substitute X with a value V, should actually evaluate at runtime to true. So this is like, this is very important for many reasons. So first, he used operational semantics, runtime semantics, to define the meaning and the denotation of types. Then he is clearly using partial correctness, right? He says, if your expressions evaluate to something, then you know that it has to evaluate the predicate. But also it's very cool because you see that the denotations, the meaning of types, are just expressions. There are no implicit proofs, there are no casts, there is nothing. Expressions belong to the denotation of refinement types. So for example here, we say that 42 belongs to the denotation of integer values refined to be greater than or equal to 0, right? Without any proof or cast by the user. Okay, so let's see how Flanagan type checks this. checks this inclusion. So 42 should belong to the denotations of natural numbers. So the first thing is it asks the type checker, can you show this type derivation? The type checker is going to say, I know by the definition of the types for constants on the left that 42 is a value that is a singleton. It's a value that is exactly equal to 42, right? And you want me to prove that 42 is a natural number, so it fires subtype inquiry implicitly. The type checking says, I cannot prove that by myself, so I'm going to implicitly use type checking to match these two types. Okay, so type checking below reduces to implication. Left-hand side should imply the right-hand side. And what Flanagan is using to check the implications is, again, operational semantics, so that it matches with the definitions of the denotations. So it says that to check this implicit subtyping, I have to check that for all integer x, if x is equal to 42 evaluates runtime evaluation to true, then x greater than or equal to 0, runtime evaluates to true. And this case is fine because on the left-hand side we have a singleton, so we can do some reasoning and say, okay, like I can prove this for all x's. But the general case, like the predicates are arbitrary runtime terms that can like diverge. And also we have this gamma. We have an arbitrary typing environment. So implication is on an arbitrary typing environment. And then, like, this is interesting, like, to check this implication on an arbitrary typing environment, the hybrid types say that you have to use the standard runtime check, like left goes to true implies right goes to true, but under a theta, which is substitution from variables of the environment to expressions, and each expression should belong into the interpretation, into the denotation of gamma. So this is a very, I think it's like very pretty. It matches very well with the definition of the denotational semantics, but it's a very difficult to compute statically, right? This for all theta breaks, yes, this for all theta like breaks all the decidability of subtyping and in consequence of hybrid type checking, but that's fine. This is fine because the hybrid term on this paper says, I don't want to be static, I want to be expressive, and I want to be able to like check whatever I can statically, but then insert casts to check things at runtime. Okay, so Flanagan hybrid types gave the syntax, it gave the denotations, it gave some very nice meta theory. But everything is dynamic, very expressive but dynamic. And then liquid types come, which stands actually for logically qualified data types. And I think the biggest contribution of liquid types is that they kept Flanagan's like hybrid types all the good features, but they say we have to be decidable. So, like, very simply, like a simplification of what liquid type says, I like this implication, I like this implicit subtyping that has zero obligations on the user, but I want to check this implication with an SMT solver. And we know that SMT solver should only receive decidable questions because otherwise it becomes unpredictable. So they use this, this function that essentially says, give me expressions from your language that you can have inside the refinements and inside gamma, and I am going to approximate them in a decidable logic, right? So with this approximation, subtyping and then essentially type checking becomes decidable. And the other nice observation of liquid types is that these T1, T2, all these refinement expressions, they are not randomly introduced by the type checking rules, right? They just appear, like they propagate the specification that the user actually wrote. So the idea is that if the user writes down only refinements, T1, T2 predicates, that come from decidable logic, then the refinement type checking rules are not going to introduce anything else. So type checking is decidable because this approximation relation essentially becomes identity. And then, of course, like a big contribution of liquid types is that they use abstract interpretation and some predicate abstraction techniques to also give decidable inference of refinement types. So yes, like a big, like when we say liquid types, essentially we mean the inference technique of refinement type checking, and the requirement there is that all the specifications you use are decidable. Okay, so we have syntax and semantics, we have decidable type checking, and then 2014, essentially we put all these ideas to Haskell, because before that, everything was happening for ML. And so, 2014, Liquid Haskell. So essentially, we ported all these ideas to Liquid Haskell. We thought it was a very simple project. We know everything, let's port it. And the interesting thing is that under the lazy evaluation of Haskell, refinement types became unsound. So in this paper, we have an example that we say, if we just apply the type checking rules we have, like laziness creates a big unsoundness. And what we did, like the easy solution we had to overcome this problem, essentially we used refinement types to build a termination checker, and we say you can only trust the refinements of the expressions that terminate, and if they terminate, we don't really care about the evaluation strategy. Okay, so we have the Liquid Haskell implementation, and we said liquid types are very good because they gave decidable, efficient type checking, but they really restricted the expressiveness power of verification with refinement types. So the next important step in Liquid Haskell was this refinement reflection. And refinement reflection essentially allows the user of Liquid Haskell to use any terminating user-defined functions into the specifications. And also, they provide this PLE, proof evaluation technique, to automate reasoning when you use user-defined functions. Okay, so let me give a quick example of PLE, of reflection, because it is easier than explaining it. So again, we are in Liquid Haskell. I call this like the moment like you have this reflection flag, you can turn it on. The moment you turn it on, I call this deep verification because it's not intrinsic anymore. You prove externally properties of user-defined functions, right? And yes, so here you can reflect your user-defined function. For example, here I am hiding append from prelude. I am defining my own append, and I reflect it. And reflection essentially means you can put it into the logic. So here I use refinement types to describe a theorem of append that says for all input list x's append to the empty list is x's. And I can use Haskell to prove this theorem. The proof goes, let's see, I think usually the proof goes by copilot. Yes. So the proof is inductive. So I split cases. I have my empty case and my cons, and I say, okay, like, can you prove this? Copilot, okay, I have done many proofs. So it knows me, and it knows that most of the proofs go by induction. But Liquid Haskell says, no, 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 that's not enough. And here we are in a world that we have like very complicated specifications, so the types are not very helpful, but what is helpful is the line, right? So it says line 12, I cannot really prove it. And we can use this proof combinators library to do equational style proofs, right? So we can say x's is the empty list, append it to the empty list, is equal to the empty list right-hand side, QED. And these like equal QED are proof combinators that come from Liquid Haskell. So it liked line 12. It doesn't like line 13. So, these are, no. Yes. OK, so let's try to fix this. This case, again, we can go by equational reasoning. We say, yes, left-hand side is this, equal, equal, equal this. And now we can apply the inductive hypothesis, right? So equal, 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 yes, by inductive hypothesis, we write X is append empty list, and this completes our proof. And all good, we can do equational reasoning in Haskell. And yes, as I mentioned, like this paper, the reflection paper introduces this technique that is called PLE. So somewhere here, yes, somewhere here I have the PLE flag. I can activate PLE, and PLE essentially says you don't have to do logical evaluation. You don't have to do the evaluation steps. I'm going to do them for you. And you see, like, the base case is proved by evaluation steps. So I can just say unit, and it's nice, it's accepted. And the inductive case has evaluation step, inductive hypothesis, evaluation step, and yes. And so this is a good proof. So yes, like Copilot was trained by PLE. So this is an inductive proof. I split in the two cases, and then I just call my inductive hypothesis, right? And with PLE, proofs are very easy. So I think, yes, I can do one more. I can do the standard associativity proof. I have three lists, X's, Y's, Z's, and associativity of append says the result is the same if I append first Y's and Z's, and if I append first X's and Y's, right? So I have proof by logical evaluation on. So my proof is just an inductive proof. I don't know what, yes. Copilot is cool, but it wants to do more things. Yes, and this, like, proof by induction, I split cases. In the inductive case, I have my inductive hypothesis, and this is a good proof accepted by Liquid Haskell. And as I said, we have termination checker. We actually have, how is it called? Totality checker. So if I omit a case, I get a totality error, which means that like these proofs have the notions of mathematical proofs because they are complete. Okay, and this was the contribution of refinement reflection in Liquid Haskell, which essentially lets you expand, like drastically expand what you can put inside the refinements. So yes, like the question that we have is what can be expressed with refinement types. And the answer is, like, by default, without any extensions, without any fancy features like refinement reflection, your logic should be within the SMT decidable theories if you want to have decidable checking and decidable inference. That like inference, like if you don't have it, you really understand that you need to have inference. And like these decidable logics actually can go, like, can push a lot expressiveness. So safe indexing is the standard example, but you can use sortedness. If you use like uninterpreted functions of SMT, if you use them properly, you can express like great concepts and stay in the decidable fragment. And the good thing is that SMTs like expand what you can express. So data types were introduced like a few years back, and like you have strings, you have a lot of things in these decidable theories. And then if you use refinement reflection, I saw like this example, you can do equational reasoning, but then refinement reflection tells you you can use any data definitions and any terminating functions into your logic, which means that you are able to express and verify like many domain-specific properties, but you are on your own. You have to prove your stuff yourself. And like we have worked a lot on expressing these domain-specific properties. And an area that, like, I don't know, I like to verify a lot is this security, because it has very, very well-defined properties and very interesting and well-defined properties that you can express. And let me show you an example. So you have programs that manipulate data, right? Data exists in a database. And what can happen when you want to enforce security verification? Data can be protected by various policies. So you can have data that are secret, read, or data that are public. And So in these domains, you have this property that's called non-interference, and essentially it says that different labels cannot interfere with each other, right? So if you have a program that is supposed to manipulate public data, the result of this program cannot depend on your secret data. And so LWeb is an application that is developed, a library that's developed at University of Maryland. It builds on top of the LIO IFC Haskell library. And what it's doing, it is using runtime checks to enforce non-interference. And what we did is we proved that indeed LWeb satisfies non-interference in Liquid Haskell. And the way we proved it is we proved this, that execution preserves low view. And the idea is that we have a program. The program is using data from the database, and it evaluates to a value v. And we defined a function, erasure, that says erasure of L is going to erase all the data that have that are protected with labels that are above L. So if L is public, all the private data are going to be erased. And so non-interference says that for every label and every two programs, P1 and P2, if P1 and P2 are erasure equivalents on the label L, then the result of their evaluation is also erasure equivalent. And so we expressed this non-interference property in Liquid Haskell, as we did with the associativity of append function, and we prove it for a model of LWeb. So this is very important for the development of refinement types, because this was actually our first major proof in Liquid Haskell. It was the first major meta-theoretic proof that went outside of these like toy associativity proofs, 5.5K lines of code. And actually, yes, like these properties, the security properties are very refined. So there were actually two conceptual bugs in the implementation of LWeb that we found during the development of this proof. And this was like the first big proof, and then many domain-specific proofs came. So we reasoned about resource usage, we reasoned about distributed applications, and the concept is this, that if you want to put a lot of effort, you can actually express and you can put these domain-specific properties using refinement types, reflection, and other advanced features. And if you only want to use decidable properties in the style of, say, indexing, then verification is quite easy. It is totally automated for you. OK, so we said that refinement types are designed to be practical. With features like refinement reflection, they can be quite expressive. And the next question is, are they general enough? So until 2014, most of the refinement type systems were developed for Haskell. 2014, we said, OK, let's try this experiment of porting them to Haskell. And we saw that laziness was like a feature that we need to take into consideration, right? So like after that, there are many, many refinement type systems that are designed for various programming languages. So at last year PLDI, there is Flux that is liquid types for Rust. And there, again, the same notions applied when it came to Rust core calculus, but then we needed to think a lot on how do you design, how do you adjust refinement types to reason about Rust's memory system, right? And like, again, last year, the group from University of Lisboa published in ICSI, actually, a usability-oriented design of liquid types for Java. So last year, we had two new refinement type systems. And actually, in the next session, there is a new refinement type system presented. It's called Marvelous, and it refines Lustre programming language that's doing synchronous programming. So there are many refinement types coming out like these days, which is exciting. And what is more exciting is that the general principles of refinement types, when it comes to like the core calculus of each of these programming languages, are the same. They are the same that were used in liquid types, in hybrid types, in Liquid Haskell too. And like we wrote a tutorial of refinement types with Ranjit that describes exactly that. It says, like if you want to design refinement types for your own programming language, what should you do for the core calculus? But then, of course, you need to adjust these general principles to take care of the specific features that each language has. So yes, and with all this programming, with all these refinement types that are coming up, I guess we can conclude that they are also general. And the last question is, are refinement types sound, right? Okay, so let's go by the basics and say that the type system in sound, what it only accepts programs that cannot get stuck, right? So we can use math to express that, and we say that if an expression is 0 type checks with a refinement type T, and E0 evaluates to an expression E, then either E should be a value or E should step, right? This is the standard definition of soundness. Okay, so the cool thing is that we used like reflection and other nice techniques and expressed this theorem in Liquid Haskell. And yes, so we use this has type property, and has type, the property models a refinement type checker. So this has type on the first line is doing refinement type checking. And actually, to define that, we developed something that is called, like we call it data propositions. The idea is you take Haskell's data types and you refine them to axiomatize the type checking rules. So essentially, they are like Cox inductive predicates. And like with this data proposition and the has type property, we essentially started doing constructive theorem proving in Liquid Haskell, which I found cool. And we managed to prove this soundness property. Like again, like now I believe this is the biggest meta-theoretical proof in Liquid Haskell, 10K in lines of code. So we prove it. The cool thing is that the proof is a Haskell function. So the soundness takes as input this E0 evals to E, which is an evaluation step, and the proof K splits on the evaluation step, says if it's reflexive, which means that I didn't make any steps, it is using progress, and if it did steps, it recurs, like the proof recurses, and it's using preservation to do the inductive step. And this proof went through with 10 lines of code, so we can conclude that refinement types are sound. Okay, like usually I get some objection here. So I will keep going. Yes, so there is unsoundness in refinement types, of course. And like, yes, like on the theory, like this soundness proof is proved on Liquid Haskell for a model of the refinement type checker. And in practice, in Liquid Haskell, and actually in other refinement type checkers too, like Stainless, like F-star, you get about like 5 unsoundness reports per year, where an unsoundness report is an example of a program that is accepted by your system and violates the property, right? And 5 unsoundness bugs, I don't know if it's good or bad, but definitely it's higher than Cox or ROC's unsoundness reports, which like the Cox developers say that they receive about 1 unsoundness bugs per year in the kernel. And so the explanation on that is that Liquid Haskell implements some core, the core that we mechanized in Liquid Haskell. So we know that like we have high trust in this, like in the inductive rules defined there. But it also implements like data types, like we haven't mechanized them yet. We haven't mechanized the coercions that exist in GHC. And like, yes, like they exist right now. Liquid Haskell sees them, it like operates on them, but we don't really know what is happening there. And we haven't mechanized inference that happens in liquid types, right? And also the other thing is that like we have a huge trusted code base that implements all this. And the bigger the code base, the bigger the unsoundness bugs, right? We don't have a kernel. We don't have a trusted kernel. And also we trust DHC, we trust an SMT, we trust our inductive rules, we trust many stuff. So let's see, like on the contrary, Coq has, like, they say, 1 unsoundness bugs per year, more or less. And the reason is that Coq has a small kernel, 15K lines of code, maybe it's reduced, that implements CIC, the calculus of inductive constructions, right? Which is reduces to set theory. And we trust that set theory is consistent. So due to that, we trust that CIC is consistent. So the only gap that allows this 1 unsoundness bugs per year is this implementation, right? And there is a nice project, the MetaCoq project, who aims exactly that. It aims to close this gap and verify this implementation and like eliminate this 1 unsoundness bugs per year. Okay, so this is a good point to compare this Coq, where Coq is like type theory, I assume, that is like, by design, it is designed to be sound, right? While refinement types by design, they are designed to be practical. Even though we both address the same problem of program verification, the design, like the road which we aim at this problem is like practicality on the type theory, practicality on the refinement types, soundness on type theory. And this like is because of the origins. Where did we start it from? So the origins, of course, say I'm going to implement CIC, a logic that we know it's consistent, while the origins of refinement types back from 91 says I want to verify an existing programming language. I want to like keep the language, the target language as it is, and try to rule out programs that create errors. Okay, and then the other important thing is that because of the practicality goal, right, refinement types do not have proofs. All the proofs are implicitly done by external SMT solvers, while in the soundly oriented Coq, all the proofs are explicit. And so, like, a good example is we saw, like, back from hybrid types, 42 just belongs to the denotations of integers, while in Coq you can express these refinement types as subset types, but then you need to use an existential to create the value and also give an explicit proof term. So, like, the denotations of Coq's, like, subset types contain, by design, these proof terms. But yes, I think the important thing is to remember that both techniques aid at the same direction of program verification, and what I would like to see in the future is like this verifier that combines both techniques. And what I have in mind is like this, that the user interacts with the practical refinement types on top of their favorite programming language, and then like there is a compiler, interpreter, translation that at the end generates these Coq proofs that are actually certified by a sound theory improver. And like I have already started working on this direction, and it's a very nice work. It's Niels, these explicit refinement types, which I see that they stand in the middle. They use refinement types, but they also have explicit proof terms, so you can go like smoother in this direction. And with this vision, I would like to thank you for your attention.
Okay, so we have plenty of time for questions. So if anyone wants to step up, please do so now.
Hi, Gergely, the Standard Chartered. So in your demo, you showed the program where you had the liquid type specification for for indexing, and then you wrote a program that didn't have enough type information, and Liquid Haskell told you that you need to add the runtime check. Well, I mean, not with these words, but basically that's what it told you. My question is, can you also do the opposite, which is that after you do make the type more expressive, can you detect the unneed for the runtime checks? Like, can you warn the user that you're checking something that is not actually needed?
That you have a runtime check that it's not actually needed. Like, we are not doing it right now. I think we can do it because this is essentially like this dead code elimination. I think GHC has a nice technique for telling you that, oh, this is dead code. You don't have to do it. So if we do integrate the target language with the information that you get from refinement types, I think you can get it. Because I mean, Liquid Haskell, again, like refinement types are very good at these decidable theories, and dead code says, I detected false. And like usually the false is easy to detect. So you could have, like I think if you extract, this information exists. If you detect false, the information exists. Like you can check is here false manually, and it will tell you yes it is, and you can remove it. So this procedure is not implemented, doesn't exist, but I think it's you can do it.
But so basically you're saying that you could like detect that all the branches except one are dead, and then that makes the check.
And I guess the way to do that, you say, can you prove false here? If it can prove false, it means like you're dead code, and then you can go and delete it.
Thank you.
Yeah, so you mentioned some Haskell features that you just have to trust, like the coercions and data types and stuff. And we keep adding new features to GHC. So I was wondering, is there some characteristic that makes are there some features that are harder for you to add to Liquid Haskell that we should maybe think about, or is it all the same and you just need some more time?
So we work on the core language. So the core language, I think it has like this pretty lambda calculus, and then it has coercions that contain everything else. Yeah. So like coercion is difficult for me because I think for me that I don't understand exactly what's happening. It is the feature that gets updated, and like my understanding is that every time a new language feature is added, it goes into the coercions. And the rest is like the rest of the core calculus of GHC is quite straightforward. So I don't know. Yes, and as I said, we accept programs that use coercions, but we don't have any argument why this is correct or not. I think it's a very nice project.
Thank you.
Hi. Thank you for the talk. I really enjoyed it. So I was wondering how you would compare the liquid Haskell reflection and inductive proposition technique, which I thought was really interesting, especially for the soundness, with the propositional universe in ATS, where you can do explicit constructions, as well as its inductive data propositions, which seem to do about the same thing.
What is the question?
So in ATS, you can do explicit propositions as well as like the inductive propositions. And you said you could do the same thing with Liquid Haskell with reflection. How would you compare the two?
I don't know. Comparison. I mean, I don't know what do you mean compare, right? Because essentially, for example, I know how to compare with Coq, but I think a legit comparison needs to have the translation, right? And at the end, if you translate between two different verifiers, it's a lot of details. So if they have the same feature, I assume they are equally expressive. But to do that, you need to figure out the details, and right now I don't know the details.
Okay, thank you.
Thank you.
You can go there. I can later.
Hello, I'm Łukasz Stafiniak from Ahrefs. I have two remarks. So first, is my understanding correct that liquid refinement types cannot show that the function post condition is inconsistent because they only verify instantiations of function applied to an argument?
Yes, we check the argument. Yes. So refinement liquid refinement types, because yes, there are in this row there are many different types of refinement types. So in Liquid Haskell, we when you make the call, you check the precondition. You don't assume it and then derive.
Well, just for a function standalone, you don't check whether the post condition is inconsistent, because I think that's from the semantics. You don't have existential types, so you need to propagate the the free variable to the post condition?
That the post condition is inconsistent. So if we can actually prove if it is inconsistent, we can prove. So I mean, if the preconditions are false, you can prove that the post condition is false too. Or like what I mentioned before, if you have like somewhere dead code, or if all your function is dead code, you can prove false. And I assume false is inconsistent. So you can actually prove it.
Thank you.
It's different semantics, right?
I need to think through it. Thank
Yeah, and like if you want to check the semantics, for me, the cleaner semantics is the hybrid type that defines the denotation, and everything is defined there very smooth. And yes, like you can, like it's partial evaluation. Like from Flanagan semantics, if the expression terminates, then you need the post conditions to evaluate so you have this partiality, you have this if, so you can prove false.
Thank you. So the other remark is, Haskell and OCaml have GADTs, which have existential variables and reasoning by cases. So they are an orthogonal specification mechanism. How do liquid types interact with GADTs? Is there like forbidden to cross them, or do they interact?
It's not forbidden because, as I mentioned before to Matti, we verify core. And in the core, everything is desugared. So the data types are essentially, like we have case, and then we have the type constructors that carry away all the information. So Liquid Haskell doesn't know that it is doing GADTs, but also, like as I mentioned, we have not mechanized the proof for data type. So I assume, like when we do that, we are going to understand better exactly what this interaction.
Thank you.
Thank you.
Yeah, I'll let you go.
Yeah, so great talk. I have a question kind of about maybe more the practical side of refinement type checking, which is that in using Liquid Haskell, I feel like the perennial error that you get is something with a big complicated refinement type does not subtype something else. And I'm sure that in general, it's going to be hard to sort of localize that error more. But I'm wondering if there are any sort of like very common use cases that you've identified as like low-hanging fruit to potentially, like if you were to specialize that inference, or if you were to specialize as sort of the analysis of whatever error you get back from the SMT solver, you could report like, maybe on, instead of saying like at the call side of this function, you have this huge refinement type and it doesn't subtype what's output, maybe you can localize some other part of the code and say, your error is over here.
We have a good error location. The error messages are generally not very good, but error location is good because we have bidirectional bychecking, which means that we check the preconditions every time you apply the function. So there are two main ways to get an error. Either at the call side, the argument does not satisfy the precondition, and you get the error exactly at the argument, or a function definition doesn't satisfy its specified body. So you have these two cases only that generate errors, and the error messages are, the location is good. Now, like what you said, these very big error messages, like in the original example, this is why I was happy and I mentioned the error messages are still good. So if your specification is clear and it's very simple, the error messages are fine. If they get complicated, they are not. But actually, at TUPSLA this year, there is a work that is, I think, for like, yes, there is a work that is it's trying to generate examples from the error messages. And we have done this in the past. It was not very satisfactory because, again, like when the specifications get complicated, it's very difficult to explain. But this work at TUPSLA, it's refutation-based. And it's not merged yet in the Liquid Haskell, but we are trying. We are trying to explain errors better, but it's very difficult.
Yeah, thanks.
Okay, I think we have time for one more question. So Andy, why don't you go, and the rest of you, maybe you can talk with Niki during the break.
Okay, Andy Gordon from Cogna. Niki, fabulous talk. I love it.
Thank you.
I want to ask about usability and where you think the challenges are for the future. I think you mentioned there's this paper on usability, or doing research on that was for liquid types in Java. But I wonder what you think the challenges are in the future.
Yes. So, like in my mind, there are these two different usages of Liquid Haskell, the ones that I saw in the demo. There is the light one, and there is the proving theorems one. I think the light one is there. Like It has been used in some Haskell code bases. I think it's there. It's easy, like everything works. If you stay in these decidable theories, I think it's ready to be used. And it has been used in Haskell, I think. I don't know about the other language. Like I like more the other part of proving theorems and all this. I find it more interesting. This is not ready to like be used as Coq is used in a real company or stuff like that. But the first part of proving automatically by SMT proving easy specifications is used.
Okay. It'd be cool to look at that in a study.
Yeah.
Perhaps you could build on the work the folks did with Java.
Yeah. We should do that.
Okay.
Thank you.
Okay, so could we all thank Niki again, and then.